G'day guys, in today's video we'll be talking about induction with sigma notation examples. Got the first example right here. Let's go straight onto it. The thing about sigma notation is basically it's just mathematical induction, but it's just been used to save up space. So you still do the same three steps, same process. So first step, let's just get straight onto it. Step 1. We'll go let n equal to 1. Same thing. Equal to 1. So LHS, in this case, it's going to be 1. R equals to 1. We have 1 brackets 1 plus 1 is going to equal to 2. So if LHS equals to 2, so RHS needs to also equal to 2 for this to be true for n equals to 1. RHS, I'll just do it at the bottom. RHS in this case, same thing, 1 brackets 2 brackets 3, all upon 3, right here, 3 gone, equals to 2. Therefore, LHS equals to RHS, which is equals to 2. So true for n equals to 1. True for n equals to 1, step 2. Assume n equals to k in this case. N equals to k, same thing. We have k, r equals to 1. We go r brackets r plus 1 equals to, sub it in here, k brackets k plus 1, k plus 2, all upon 3. Prove for n equals to k plus 1. Same process, sub it in, k plus 1, sigma r equals to 1. So we have r brackets r plus 1 equals to k plus 1, k plus 2, k plus 3, all upon 3. Got that part. Come over here to solve this now. Rewrite this as LHS equals to, sorry, my bad, sigma. Rewrite it as k plus 1 equals to r equals to 1. We have r brackets r plus 1 over here. Come down. We have k r equals to 1. R brackets r plus 1 plus k plus 1, correct? And then k plus 2 plus 2 in this case. K plus 2, this we already know equals to this over here, so let's just sub that in. We have k brackets k plus 1, k plus 2, all upon 3, plus k plus 1, k plus 2, k plus 1, k plus 2 in this case. Next thing, just simplify this further, multiply both sides by 3, so we have k brackets k plus 1, k plus 2, plus 3, k plus 1, k plus 2, all upon 3 in this case. So we've gotten a 3 at the bottom. We've got the denominator. Next step would be rewrite this as k plus 1, correct? K plus 2. And then this third part we can rewrite as k upon 3 plus 1. In this case, write this k plus 1 plus 2. This then becomes k plus 3 all upon 3 right here, which then equals to k plus 1 k plus 2, k plus 3. But since it's all multiplication right here, it's all a product, the 3 just then becomes the bottom. So there we go, all upon 3. Therefore, RHS equals to RHS in this case from here. Now, step 3, final note to ourselves. We know that the result of this is true. So result true for n equals to k plus 1, correct? And is true when n equals to k and n equals to 1. Therefore, by mathematical induction, by mathematical induction, true for n greater than or equal to 1. Apologies for my handwriting, but yeah, that is how you do example 1. Now we'll go on to another example, so example number 2. For this next example, a little bit more challenging than the previous one that we've just done. So before we start anything for this example right here, we need to understand that this is just the nth partial sum of a sequence. So sequence of, let's just denote t of j equals to negative 1 to the power of j squared. So this then becomes some sequence n equals to, if you got the sigma notation, and j equals to 1, we have t of j in this case. Another thing I would say to note down is the case of s n plus 1, which we can also write as s to the n plus t. We have n plus 1 in this case. Now, the 3 steps of induction. Step number 1, let n equal to 1 in this case. LHS gives me negative 1 all squared brackets 1. Sorry, it won't be squared, that'll just be just be 1, my bad. That's just going to be 1 in this case. And then we have j in this case is just 1 to the power all squared. Negative 1, it just gives me negative 1 in this case. RHS, right at the bottom. RHS in this case, coming back to this over here. 1 upon 2, we have negative 1 to the power of 1 brackets 2. Negative 2 on 2, which is negative 1. Therefore, true for n equals to 1. True for n equals to 1. Coming back to step 2. Assume n equals to k in this case. So k is then this over here. We have 1 upon 2, negative 1 to the k. My bad, negative 1 to the k. K brackets k plus 1. That is for n equals to k. Prove for n equals to k plus 1. N equals to k plus 1. So s of k plus 1 in this case equals to 1 upon 2, negative 1, k plus 1 multiplied by k plus 2 in this case. Yep, k plus 1 would be k plus 2. LHS equals to S of k, as we'd figured out over here, is this one over here. S of k plus t k plus 1 in this case. LHS, again, same thing. 1 upon 2, this one over here, negative 1 to the power of k. We have k plus 1. We'll bring out the k on the other side, sorry. So k plus 1 multiplied by k is the same thing as k plus 1. Plus this one over here. Plus, negative 1 k plus 1 brackets k plus 2 in this case. Expand this, we have 1 upon 2, negative 1 to the k, correct? K plus 1 plus negative 1 to the k multiplied by k, followed by k plus 2, right? Rewrite this as 1 upon 2, we have negative 1, the k plus 1 right here, brackets, negative k plus 2 k plus 1. When we simplify this at the top, bottom then becomes 1 upon 2, negative 1 k plus 1, brackets, k plus 1, k plus 2, equals to RHS in this case. Therefore, step 3, by mathematical induction, true for n equals to k plus 1, true for n equals to k plus 1, true for n equals to k, n equals to 1, hence true for n greater than or equal to 1 in this case. That is how you do example 2. Little bit different, but yeah, still get this.